Okay, so it's my pleasure to introduce our next speaker, Marlies Gerber from Indiana University, and she will speak on non-classifiability of K-automorphisms.
Thank you. Thank you very much to the organizers for giving me this opportunity to speak and in general for this very nice conference. And I also thank the audience for persevering to the last talk of the day. And also I want to thank my Zoom audience for being here. So the first part of my talk is going to be sort of an introduction to the basics of descriptive set theory that's relevant to my talk and Borel equivalence relations. So I probably should apologize to Matt Foreman, who's in the audience, because most of this is taken from his surveys. But I hope that there will be some new things at the end. Okay, so let me start. I'm going to be talking about a very old problem, the isomorphism problem, which was introduced by von Neumann in 1932. And as the problem says, to classify ergodic transformations up to measure isomorphism. So let me define that. So measure isomorphism between two probability spaces is an invertible map, ignoring sets of measure 0, such that the map and its inverse are both measure preserved. And two transformations, T and S, are isomorphic if there is an isomorphism between the spaces such that S is conjugate to T in that way. S is equal to B composed with P composed with B inverse. And we will be considering this equivalence relation, and I'm going to write it as with this congruent symbol, the T congruent to S, that's isomorphism. And then we'll have a different symbol for some other equivalence relations. Okay, so what do we mean by classification? I'll be saying a bit more about this, but I have some examples where this is a classification of the kind that we have in mind. So this is the Helmholtz von Neumann classification from 1942, is for ergodic transformations with pure point spectrum. Then you can use the spectrum as a complete isomorphism invariant. And the other well-known classification is for Bernoulli shifts due to Ornstein. Two Bernoulli shifts are isomorphic if and only if they have the same measure theoretic entropy. So for these two classes of transformations, we have a nice way of classifying them up to isomorphism. Okay, so in general, to talk about classification and what kind of classification we want, it's convenient to have a topology on the measure preserving transformations. So we will always be working on Lebesgue spaces, so something that's isomorphic to the closed interval 0, 1 with the Borel sigma algebra and Lebesgue measure. And we take the collection of measure preserving transformations, we write them as MPTs, but are all going to be assumed to be automorphisms, so invertible. And the weak topology is the one where Tn converges to T if and only if the symmetric the limit as n goes to infinity of the measure of the symmetric difference of Tn of A, and T of A is 0 for every A in the Borel sets. And this weak topology agrees with the metric topology for some complete separable metric space. So there is it is a Polish space. And we will also want to consider various subsets of this space. So it's if we take a G delta subset of M with its induced topology, it is again a Polish space. And also, if you take a Borel subset of this, then there is some metric that makes A into a Polish space, and the Borel subset of A with respect to this new metric are exactly the same Borel sets that you had before with respect to the weak topology. Okay, so this is also borrowed from Matt Foreman's survey. What do we mean by classification and what a classification isn't? Okay, so if you just take the set of transformations and consider equivalence classes, then the cardinality of the measure preserving transformations is at most, well, there are a continuum many of the measure preserving transformations. So the equivalence classes, the cardinality of the equivalence classes is at most a continuum. And by the axiom of choice, then you can just using cardinality, you can get a function from the classes of isomorphism classes of measure preserving transformations to the reals, and then that will give you an invariant. But that's not very useful. Okay, so just something you could get from the axiom of choice is not going to be what we have in mind. Okay, so what do we have in mind? It's maybe not quite so clear, but we want to have something that we can get a hold of using some countable technique. And in the context of classification of measure preserving transformations, we would like at least to have the set of pairs ST in the product space such that S is isomorphic to T to be a Borel subset of the whole space cross itself. So I want to talk about Borel reduction. It's a notion of one Borel equivalence relation or an equivalence relation being reducible to another equivalence relation. So we use this little symbol, so there's curly less than. So that's saying that in a way that E is less, at most as complex as F is. And the formal definition is there that if you have two polar spaces, Y and Z, and you have equivalence relations, which we're thinking of as ordered pairs of things that are equivalent, so subsets of the product spaces, then E is Borel reducible to F, if and only if there's a Borel function that takes Y to Z such that Y1 is equivalent, E equivalent to Y2, if and only if F of Y1 is F equivalent to F of Y2. So if you want to find out whether two things are E equivalent, you map them over to the other space, to the space, and you check if they're equivalent there. So here's an example with the Ornstein's classification. If you take Y to be the collection of measure preserving transformations and Z to be R, then if you take the map from, and you take the Borel subset, that's actually not completely obvious, but the Bernoulli automorphism is the Borel subset of M, so it makes sense to talk about equivalence in this context. So if you take the Bernoulli automorphisms with finite entropy, then the map that takes you from the Bernoulli automorphism to the entropy is an example of a Borel reduction, because you take the two transformations and you look at their entropies, and then if the entropies are the same, then they're isomorphic. Okay, so that's one well, you sequence where you did the one I just talked about, where you check between two numerical invariant. Then there's another equivalence relation that comes up often. This is called E0, and these are it's an equivalence relation on sequences of zeros and ones. So two sequences of zeros and ones are said to be equivalent for E0, if and only if they agree eventually. So this is related to the Ornstein-Shields examples. These were examples of measure preserving transformations that are K but not Bernoulli. And there's a particular, I don't have time to go into the construction that's used, but there's a set of parameters. They are indexed by sequences of zeros and ones. And there's a process that you do at each stage where you do either do something in the forward direction or in the backward direction, depending on whether you see a 0 or a 1. And this exactly is two such transformations are isomorphic exactly when the corresponding sequences agree eventually. So that's an example of a reduction. So E0 reduces to isomorphism on these Bernoulli, on these K but not Bernoulli examples. Okay, so now, so we have seen now two equivalence relations, the E0 and equality on R. And there is a result, which is, well, originally due to Feldman, it's also now known as the Herring-Keckers-Leveau dichotomy. So if you have an equivalence relation on a Borel, on a Pauli space, and if this E0 is, reduces to an equivalence relation on that space, then there is no complete Borel invariant. Okay, so if you have a Borel map that takes the sequences of zeros and ones into your space, such that for any two sequences that the images are equivalent if and only if the two sequences are E0 equivalent, then you cannot get a complete Borel invariant. That's a 5-minute argument. I wish I had time to show you, but I don't. So I'm going to go on. Okay, so we have this consequence that there is no complete numerical Borel invariant for isomorphism of ergodic automorphism. And just looking at that collection of examples. So we know that E0 reduces to these Ornstein shields example. And if you had a complete Borel invariant, then there would have to be a complete, if you had a complete Borel invariant for ergodic automorphisms, you would have to have a complete Borel invariant for these Ornstein shields examples. So you would have to have the reduction you have a reduction from E0, this we know. We'd have to have a reduction from E0 to the isomorphism of Ornstein shields. And then if we had a reduction to equality on R, then that would contradict, you have transitivity of this curly less than sign. And so that would contradict the Feldman result that E0 does not reduce to equality. So this says that this E0 is, so we cannot have a complete Borel invariant for our ergodic automorphisms. Okay, but maybe we can get something else. So there's another equivalence relation that comes up a lot. This is called equality plus. And equality plus is defined on sequences of points on the unit circle. And you say the two sequences satisfy equality plus if and only if they have exactly the same points in those two sequences. And the order could be different. The order can be different, and the multiplicity doesn't matter. So each xn has to be equal to some ym, and each yn has to be equal to some xn. And so that's the equivalence relation. And it's convenient to write it like that because we can then check that it is actually a Borel equivalence relation. So that, well, I'll define that in a moment, but it's a countable collection of things to check. So now this equality plus is actually the same kind of equivalence relation as what comes out of the Helmholtz-von-Neumann theorem. So this is due to Foreman and Leveau, actually in both directions. So if you look at carefully at the proof of Helmholtz-von-Neumann theorem, then you can get a reduction of isomorphism of discrete spectrum transformations to equality plus on S1 on sequences of points on the unit circle. And in the other direction, it's also that equality plus on the unit circle reduces to isomorphism for discrete spectrum transformation. So in the last box there, we have the summary of what it says above. So equality plus reduces to isomorphism of discrete spectrum transformations, and that reduces again back to equality plus. Okay, and then another thing that we need to, so equality plus is just exactly as complex as the classification of discrete spectrum transformation. And there's another result that says that that E0 does reduce to equality plus. So equality plus is a more complex equivalence relation, and it does not. So that's the strictly more complex because it does not reduce. Equality plus does not reduce to E0. So these two kinds of classifications that we looked at, the one to the Ornstein with the numerical invariant, and the one, the discrete spectrum transformations, they have a different level of complexity. Okay, so a Borel equivalence relation is simply one that where you look at the set of pairs of points that are equivalent, and that forms a Borel subset of the product space. And if you have two polar spaces and two equivalence relations, and E reduces to F, and the second one is Borel, then E has to be Borel, just because the inverse image of a Borel set under a Borel map is Borel. So in particular, E reduces to, if E reduces to E0, if whatever equivalence relation you have reduces to E0 or equality plus, because those are easy to show are Borel equivalence relations, then the equivalence relation that you're looking at would also have to be Borel. So if you hope to have a simple classification using E0 or equality plus, then that's sort of the minimum requirement. Okay, so then with this criterion, then we see that actually this isomorphism relation is not Borel. This is a result of this. The first one is a result of Gerber from 2001. So the notation here is that we have a Lebesgue space. Ergodic on Lebesgue space, and we have measure preserving transformations, and then we have our E of X. This is our ergodic ones. So we considered first in the first result, they're just the measure preserving transformations, and those turned out to be a complete analytic set. I will explain what that is, but for right now, the important thing is that it's not Borel. And so this result was a nice breakthrough, but it was also not clear from this whether that what that would imply for ergodic transformations, because his transformations were highly non-ergodic, and it seemed like it might be the case that the complexity of the equivalence relation on the measure preserving transformations just came from how complicated a way you put together these ergodic components. So the next big breakthrough was by Foreman, Rudolph, and White in 2011, and they proved that it's also not Borel if you consider just ergodic transformations. So after this, the natural questions that came up were, well, what could you say for maybe smooth dynamical systems? Maybe if we restrict it to classification of ergodic transformations that could be realized in a smooth way, maybe we could say something. That was a very interesting question related to the the realization problem, because if it had turned out, so the answer here is no, that it's still not, so the same result, but not being Borel also holds for smooth dynamical systems. But if it had turned out the other way, if there were a Borel way of mapping abstract ergodic transformations into their smooth realization, and you could get, and the smooth realizations the equivalence relation of isomorphism on that were Borel, then and the other one and the original one is not Borel, so you would have abstract proof that there exists something that cannot be realized in a smooth way. Okay, so then I'm also going to talk a bit about other equivalence relations and also specific classes. So we have now the general class of measure preserving transformations, and we have the ergodic transformations, but there are a lot of other classes. So maybe if you restrict to something more, then we might be able to get a classification, or at least that's the problem. Oops, no, going the wrong way. I'm going backwards, I think. Oh, I have it upside. Thank you. Okay, so the ergodic automorphisms. So that's a density delta set of the subset of the measure preserving transformations. Weakly mixing automorphisms are also a density delta set. Both of those are in Helmholtz's text, and the second one was in a paper of his from 1943. Mixing automorphisms could be considered. Maybe those could be classified. Those are a meager set. And so if you look at these two results, that gives you an abstract proof that there is something that's mixing, but not weakly mixing. So now there are also concrete examples. There is one that came just a year later after Reuchlin's result. That's not so well known, and the one that most know is Chacon's example from 1959. Okay, and then another class of automorphisms that we could consider the ones the subject of my talk is collection of K-automorphisms. These were defined by Kolmogorov in 1958 in terms of a 0-1 law. I'm taking the kind of an easier way of describing them. So this is according to the Reuchlin-Sinai theorem. T is K-automorphism if and only if every non-trivial factor has positive entropy. And Foreman actually used both of these characterizations to prove that the set of K-automorphisms is a Borel set. Okay, so for the next slide, I'm going to need this definition. I'm going to be defining Kakutani equivalence. So for this, we need the first return map. So the first return map to a set is so you take this, it's written as T sub A. So T sub A is you just take I can't draw on here, but you probably are familiar with this. You take a point and you look at its iterates under the forward orbit of T, and you take the first time when you return back to the set. And then you take the induced measure, the measure restricted to the set A, and you normalize it. So that gives you a new transformation. Okay, so we were talking about K-automorphisms. How do we get K-automorphisms? There are quite a few results of this type, how to get them. There's one due to Melanson in 1974. He has certain skew products over a Bernoulli base. We were able to use this we have two versions of our result. One is for automorphisms, and then one is in the smooth case. So in the automorphism case, this was all we needed. And this next thing is something that's an interesting fact. It's actually not used in our proof, but if you take any measure preserving transformation with positive entropy, then you can induce you can find collection of sets that you can use to induce. In particular, you can take one that's has measure arbitrarily close to 1 and get K-automorphism. And then in the smooth case, this is a result that we do use in Patak's result from 1980, is that if you take, that there is a way of constructing non-Bernoulli K-automorphisms on manifolds of dimension at least 5. And then a more recent result of Konagovsky, Rodriguez, Hertz, and Vinich from 2018 gives a way of constructing smooth models of K-automorphisms in dimension 4. And they also have the property that they are what's called loosely Bernoulli. Loosely Bernoulli is Kakutani equivalent to Bernoulli in this context, but they are not Bernoulli. Okay, so okay, so this is the question that Foreman asked in his survey. These two surveys are extremely helpful for anyone who's interested in the subject of dynamics and descriptive set theory. So in those two surveys from 2000 and 2022, he asked, what if you consider the K-automorphism and restrict the isomorphism relation to K-automorphisms? Okay, and is that a Borel set? So if it were a Borel set subset, then you might. What? These surveys, yeah, Foreman, in these two survey papers, Foreman asked the question. So Foreman is the author of the survey papers, yes. Thank you. Yeah, so he attributes this, or actually I've seen this attributed to Neuberger in a later, actually we have another version of this question appeared in the BAMP conference list of questions, and there it was attributed to Neuberger. And so now our answer is that no, it is not a Borel set. So we get the same kind of result, that is the complete analytic set, and that implies not Borel. Okay, and then another thing that one could ask is, well, okay, so maybe we can't classify all the measure preserving transformations or all the ergodic ones or all the K ones, but maybe you can, if you have a K, not generic, of course, because mixing is it implies mixing, and mixing is already not generic. But if you take, what if you just restrict to a dense G delta set? And Foreman and Weiss proved that you cannot Borel reduce this to equality plot. They proved a lot more, but this is what, in the context of what I've explained so far. So that was the most complex equivalence relation, a Borel equivalence relation that I discussed. So you can't reduce it to that, but there is one positive classification result, which is also in this paper of Foreman, Ridolf, and Weiss. It's based on a work of Jonathan King from 1986. And he proved that, or they proved that for rank 1 transformations, which I also don't have time to define, but basically that you can do a cutting and stacking construction where you have just one column at each stage, and the levels generate the sigma algebra. Okay, and for such transformations, the isomorphism equivalence relation is in fact Borel, but there's no nice, there's still no useful structure, no useful, right? No equality plus, obviously, and there's just no other known useful way of classifying it. Okay, there are also some related results in a different context. You can also talk about topological conjugacy, and Foreman and Gordetsky in 2022 proved that if you consider the topological equivalence relation of conjugacy on C infinity diffeomorphisms on any closed manifold, that's not Borel. The paper is written for dimension greater than or equal to 5, but they subsequently improved it and were able to get this even in dimension 1. And then I want to mention a result of Philipp Kunde. This is for circle diffeomorphisms. You can, instead of topological conjugacy, you can take topological conjugacy where we require some smoothness of a certain level of smoothness. And he proved that there is no complete numerical Borel invariant for this equivalence relation. Okay, so then we have other equivalence relations, which I haven't talked about yet. So instead of isomorphism, we can consider another kind of equivalence relation. So to define this, it's useful to talk about the special flow over transformation. And I suspect you are all familiar with this. So you have a transformation T on the base. So then you flow up to the top to your root function, and then you instantly go back down to the T of X. Okay, so that's the special flow over T. Okay, oh, and this, if you have a flow like this, then what's on the base here, this base transformation, that's called a cross section of your flow. Okay, and then Ambrose-Kakutani theorem tells you that any measure preserving flow is going to be isomorphic to a special flow. Okay, and then Kakutani equivalent of two ergodic transformations is you can take either one of these as your definition. These are equivalent conditions that your transformations are isomorphic to measurable cross sections of the same ergodic flow. Or the other way of formulating it is in terms of the induced maps T to A and S to B. So if there exist sets of positive measures so that the first return maps are isomorphic, then these two are Kakutani equivalent. And that's now written with the symbol similar. Okay, and I'm going to skip the motivation, but it had to do with if you want to classify flows up to time change along orbit, then that's the same thing as classifying transformations up to Kakutani equivalent. Okay, so we have the definition again. There's the induced transformation and two transformations are Kakutani equivalent. That's one of the versions that I got before. Now, the question was originally, well, because the other thing is Kakutani equivalent, but Abramov's formula tells you that in order to be Kakutani equivalent, you have to have to be in the same entropy class. Either both have entropy 0, both have finite positive entropy, or have infinite entropy. And then Feldman's work proved that this is not enough to classify things up to Kakutani equivalence, that there are at least two non-Kakutani equivalent ergodic transformation in each of these classes. And then Ornstein, Rudolph, Weiss proved that there was an uncountable family in each of these entropy classes. Okay, and then there's also a notion of even Kakutani equivalence. That's the same as Kakutani equivalence, except that we require that the sets that you induce on the A and B have equal measure. And then when that happens, then we write this equivalence with a little e above it for even Kakutani equivalence. Okay, so we have an earlier result for our anti-classification with respect to Kakutani equivalence. And that says that, the Kakutani equivalent relation is a complete analytic set and therefore not Borel. Okay, and it's also true for even Kakutani equivalent. Okay, and yes, we also have this for C infinity, just as in the case of the Foreman Weiss results. This is also true when you restrict to C infinity diffeomorphism or real analytic, even real analytic diffeomorphism. Okay, and then we have a notion of reduction for set. So a function reduces a set A contained in X to a set B contained in Y if the set A is F inverse of B. And if your function is Borel or continuous, then it's called a Borel reduction or continuous reduction. So it's also a measure of how complicated the set. And an analytic set is a continuous image of a Borel subset of a Polar space. It doesn't actually matter. I could also say Borel image as well for a Polar space. That's the same thing. And complete analytic is a set such that every analytic set can be reduced to A by a Borel function. So because there are known to be analytic sets that are not Borel, a complete analytic set is automatically not Borel. Okay, so an example of an analytic set is our isomorphism relation, because you can take the map that takes let's say an ergodic transformation T and a invertible measure preserving transformation B, and you can take this pair T and phi T the inverse, and that gives you everything. By taking different phis, that will give you everything pairs that are of T and everything that's isomorphic to T. Okay, so now I want to talk a little bit about trees. So in order to get an example of a complete analytic set, I'm going to actually draw this for an example. So I want to just find what a tree is, because we need that for our description here. So let's suppose we have, so trees are subset. I think I have that already. So a tree is a subset of the collection of all finite sequences of natural numbers. So let's suppose we have two sequences, 5, 8, and 3, and we have another sequence, 5, 1, 7, and 9. Okay, so these are elements of finite sequences, and the tree associated to that to those sequences would be you would start with the empty set. So that everything starts with the empty set. This is an example of a rooted tree. And then at level, this is level 0. And then at level 1, you would have just the 5. And then at level 2, you would have 5 and 8. And 5 and 1. And then you'd have 5, 8, 3. And 5, 1, 7. And 5, 1, 7, 9. Okay, so this is an example of a tree. So the property that you need here is every sequence. So I didn't write down all the sequences. So every initial segment has to also be in your collection. That's a requirement for the trees. And then let me go to the next slide. So this is an example. So those numbers there, those are not the numbers in the sequence, but that's just a way of numbering the possible nodes. So you have infinitely, you can have either finitely many or infinitely many things coming out of the first node, and then out of each of those nodes, you have either finite or countably infinitely many things coming out of that. Then the trees, the space of trees, this thing is the collection of all such trees, but you require them to have arbitrarily long finite sequences. Okay, so and the infinite, the complete analytic set, that's the example that's being used here, is the collection of trees that have infinite branches. So you have to, in order to be in the collection of trees, you have to have arbitrarily long branches. But if you have a single infinite sequence such that every finite initial segment is in your tree, then that's the yeah, that's what's called an infinite branch. And if you have an infinite branch, that's called an ill-founded tree. Okay, so the strategy of proving non-classifiability for, I said here, even Kakutani equivalence, it's the same strategy for for Kakutani equivalence and also for isomorphism. So what you do is you construct a continuous function from the trees to the ergodic transformation such that T has an infinite branch if and only if the image transformations have the property, well, the image transformation has the property that it's isomorphic or even equivalent to its inverse. And so that it follows from that the set of evenly equivalent things is a complete analytic set. Okay, so I'm gonna have to go a little bit faster because I'm running out of time. But what I want to do, so the important thing here is our strategy. It's from what's below here. If you have T has an infinite branch, then we prove that the image transformations have the property that it's isomorphic to its inverse, and then of course that implies even Kakutani equivalence because that's a weaker equivalence relation. And then going in the other direction, we prove that if they're not evenly, the transformation is inverse or not evenly equivalent, then if T does not have an infinite branch, and then it proves on or implies non-isomorphic. Okay, so yeah, I'm going to have to skip this because yeah, I want to get to the new part of this. This is still part of our old work. So the strategy for proving that if you have an infinite branch, then the image is isomorphic to its inverse, that is exactly the same as in Foreman Rudolph Weiss. We have a different map, but the proof of the isomorphism that they are isomorphic, that's the easy part. It's always harder to prove that something's not isomorphic than the proof that prove isomorphism. So yeah. Okay. So skipping ahead a little bit. So here's our new result. So this is and I phrased it in the smooth setting because that's the stronger version. So our result, this is joint with Philipp Kunde. There is a continuous map from the trees to K. So script K is the collection of K-automorphisms. So we take K-automorphisms that are also C-infinity diffeomorphisms, and they preserve Lebesgue measure that lambda 5 is just because it's in 5 dimensions. So and we construct a pair of transformations. For each tree, we get a transformation B1 of this tree and B2 of the tree. And we follow the same strategy. If T has an infinite branch, then we'll get the B1 of T and B2 of T to be isomorphic and therefore Kakutani equivalent. And if it does not have an infinite branch, then we will prove that they are not Kakutani equivalent. And then we get the same corollary that it's a complete analytic subset of the diffeomorphisms, cross diffeomorphisms. Okay, and there's another result. I don't really have time to go over this, but Philipp Kunde has another similar result for weakly mixing, and he's able to do this for T2. So our construction, current constructions is for T5, but he's able to do it for T2, which is nice. Okay, so here's the outline of what I have 3 slides left. So, and I did start 3 minutes late. So, okay, so we have to construct these maps, the B1 and the B2. So here's the way that we construct it. So this again at the top is just a repeat of what we're trying to do. So what we do is we take, this is not a repeat. This is our previous result. This is our previous result. We were able to get a continuous map from the trees to ergodic transformations that are C infinity diffeomorphisms, such that again that the images are the transformation and its inverse are isomorphic if there's an infinite branch, and they're not Kakutani equivalent if there's no infinite branch. Okay, so the new part. So we're going to take our transformation from the f of t that we got before, and then we take the special flow over t with root function 1. And then we were getting ready to apply Katak's result. We take the C infinity function from the torus to the reals, such we're going to take we're nearly constant. And we also require to have the periodic trajectory of some period k, where the sum of the values of the function along the periodic trajectory are not equal to the k times the integral. And this is the condition that will prevent the function phi to be cohomologous to a constant. So that's the hypothesis that's needed for applying Katak's result. So Katak's result said that if you take this O and G, I think maybe I didn't put it, but anyway, G is a Nosov. I've made that correction, but anyway, G is a Nosov. T2 to, well, I can't write it, but yeah, let me write it here. So G maps T2 to T2 is a Nosov. You can, it doesn't matter what you can take it to be linear. Okay, so this map, according to Katak, is K-automorphism. Okay, so we have, I just repeated the definition. So what we do is we take this skew product, the TG phi, and that's our first function. And for the other one, we start with T inverse, and then we do the same thing to it. So if the T and T inverse are isomorphic, then after you do the same thing with the G and the phi, the G and phi are not dependent on the tree, then they will still be isomorphic. Okay, so if we have, so by Katak, we have these image transformations are K-automorphisms. And we know that if T has an infinite branch, then T and T inverse are isomorphic, and that means that phi1 of T and phi2 of T are isomorphic. And so the last thing that I need to do is explain why if the T does not have an infinite branch, that they are not Kakutani equivalent. The phi1 of T and phi2 of T are not Kakutani equivalent. So we know that if if we suppose that T does not have an infinite branch and we take the image from our previous construction, then we know that T and T inverse are not Kakutani equivalent. Now we're going to construct the flow over G with using phi as our root function. Then if we, and G was our Nosov, oh yeah, here's where I have it, a Nosov diffeomorphism. And this flow is an Nosov flow. And because this function phi is not cohomologous to a constant, we know from a Nosov alternative that every stable and unstable leaf will be dense. And then from Banamovich result, is that for such an Nosov flow, that it will be a Bernoulli flow. So in particular, the time one map is Bernoulli. Okay, so then what we do, our final step is that we take our phi1. So yeah, so this is where an idea of Jean-Paul Survenot's comes in, and we found this in the paper of Konagovsky, Rodriguez, Hertz, and Vinich. So they show that if you have this skew product, the T G phi, that is Kakutani equivalent to T cross the time one map of this Nosov. And this Nosov is this time one map of that Anasa flow is a Bernoulli by Banamovich. So we get Kakutani, so B1 of T will be Kakutani equivalent to T cross B, and B2 of T will be Kakutani equivalent to T inverse cross B. Okay, and we know that T is not equivalent, not Kakutani equivalent to T inverse. So we need some kind of a cancellation law. So there is a work, and then this is related to actually a question of Jean-Paul's that he asked if you know that if you knew that T cross B is Kakutani equivalent to T inverse cross B, could you cancel and say that? So the question is if T inverse cross B is Kakutani equivalent to T cross B, does this imply that T inverse is Kakutani equivalent to T? And so that is a question that we do not know the answer to, but we were able to show in this special case, and this is actually very similar to an argument in Ornstein, Rudolph, and Weiss, although it was more complicated because we had to work with equivalence relations instead of equivalence classes instead of individual words. But we were able to show that if T is not Kakutani equivalent to T inverse, then T cross B is not Kakutani equivalent to T inverse cross B. So that's the outline. That's the main addition technical part of our new work. And there's one question that is still open, sort of natural question. Well, we can't classify K-automorphisms, but what about if we added this additional assumption that they are loosely Bernoulli? Maybe, so of course, they're all in the same Kakutani equivalence class, so our strategy doesn't work. But is it possible then maybe those could be classified up to isomorphism? So we know from Feldman that there's no numerical Borel invariant because the Ornstein-Shields examples were all loosely Bernoulli. Okay, thank you.
Thank you very much. Are there any questions, comments? Yes. So what would be your intuition on your open question?
Well, so far, everything that we've looked at has not been classifiable. So I would expect the same thing, but yeah.
I see. So let's thank Marlies again